Physical database design is different from logical database design because the focus is different. In physical database design, the focus is on performance. We are going to consider how to store database in the secondary storage device, and we are going to consider how we are going to store them in a way so that the data can be accessed efficiently, can be queried efficiently. So that's the concern of the physical database design. In the physical database design, we are going to consider a number of things. We are going to consider how to optimize the database at the field level. For example, what kind of field type or data type we are going to use for the field. What's the size we are going to give the field. And then we are going to try to optimize the database at the record level, and then to the file level, and then to the database level. So we are going to consider optimizing the database at all these 4 different levels. Some of the topics we are going to cover in this chapter include the physical database design process, the storage format for attributes or data types for attributes, what's the appropriate file organization, what's the different types of file organizations, how to use index, things like that. So those are some of the topics we are going to cover in this chapter. And also in real world, when you go through the physical database design, you will also consider issues such as security, backup, and recoverability. Since these topics will be covered in another chapter called Database Administration, we are not going to cover these issues in this particular chapter. So what is physical database design? Well, the purpose of the physical database design is to translate the logical description of the data, which we got from the logical database design, into the technical specifications for storing and retrieving data. We are going to specify how we are going to store the data physically on the hard drive. So the goal is to create a design for storing data that will provide adequate performance. Obviously, what's adequate will be different from one organization to another organization. You need to first investigate what's adequate performance to your organization before you go into the physical database design. And you want to ensure the database integrity, security, and the recoverability during the use of the database. So that's the goal of the physical database design phase. So what's the physical database design process? Well, you take a number of inputs you get from the previous steps and then make a number of decisions. The inputs you get normalize the relations. That's what you got from the logical database design. Volume estimates, you probably get that from the analysis phase. Attribute definitions, response time expectation, data security needs, backup recovery needs, integrity expectation. All of these you probably get from the analysis phase. Using these inputs, you are going to make a number of decisions. You are going to make a decision about the data type. You are going to make a decision about physical record, make a decision about the file organization, make a decision about which field you are going to index, and also make decisions about how to optimize the query. These are the decisions you will make based on the inputs you get from previous steps. This picture is a usage map for a database. It's similar to an ER diagram, except it doesn't have the attributes, and also it has all these numbers here and the percentage here. What do these numbers mean? Well, they basically mean the volume of the database tables. For example, the number 1000 here, it means that there are 1000 records in the part table. There are 400 records in manufactured part table. There are 50 records in the supplier table. And then these numbers outside the rectangular boxes are the usage data. The 200 here means that there will be 200 queries on the part table every hour or every day, depends on the unit you use. Of the 200 queries for the part table, 70% of them, or 140 of them, will also access the purchased part table. There are 75 query on the supply table, and of the 75 queries, 40 of them will also access the supplies table, and also 40 of them will access the purchased part table. These numbers show the volume of data and also show the usage frequency of this data. These numbers are usually estimates. After you have used the database for a while, you get a pretty good idea of what these numbers are by observing the log for database activities. But during the development process, these numbers are usually estimates. The important information you need to get is the relative number instead of the absolute number. What it means is, well, it's not important to me that there will be 60 queries on the purchase part. What's important to me is that the access to the purchase part through the part table will be more than twice as many as direct access to the purchase part table. Does that make sense? It's the relative number that's important to me because I want to know which table is accessed more frequently, which table is accessed less frequently. So based on this volume number and the usage number, you can make a number of decisions about physical database design. For example, as you can see, the supplies entity or table has 2,500 records, much larger than any of the other tables. So maybe one physical database design decision you can make is, well, we probably need to put supplies table on a computer with a larger storage device and more processing power. Also, pretty much every time when the supplies table is accessed, we also need to access the purchased part table. There are 40 access to the supplies table, and all of these 40 access will access the purchased part table. So maybe what we can do is we can do something called denormalization, which is the opposite of normalization. Normalization is decomposing a large table into smaller tables. Denormalization is to combine smaller tables into large tables. So maybe we can combine the purchased part table with the supplies table into one table so that we can avoid joining these tables when users access these two tables. And also sometimes it's important to understand how the users access the data. For example, which field do they usually use to search for suppliers? Which field they use to search for parts, right? Because that will tell you which field you should index in your database. So those information are very important when it comes to physical database design. In physical database design, one of the decisions you need to make is to find the best storage format for fields. The storage format is important because it will determine the efficiency of the storage space usage, determine the ease of retrieval of data, and also will determine the accuracy and integrity of the data. Field is the smallest unit of the data in database. In field design, there are a number of decisions you need to make. The first decision is to choose the right data type. To choose the right data type is very important because that's going to determine how efficient your database is during processing. Here we have a list of common data types. We have the fixed length character, variable length character, long number, integer, date, and the blob, which stands for binary large object for graphics, sound clips, movie clips. Usually it can hold about 4 gigabytes of information. For different database management systems, they also have different data types. And the second decision is to consider whether you need to code the field, compress the field, or encrypt the field for security reasons. In this example, we are coding the field finish. In the product file, we have a field called finish, and the finish can be birch, maple, or oak. So in this case, instead of having the value, actual value, birch, maple, or oak in the table, we decide to use ABC to code it. So why do we do that? Well, if we do this, this is going to reduce the file size for the product table because now we only need one character instead of multiple characters for each finish. The decision you need to make is whether it's worth the trouble to code the data. In this case, you have to look at the data volume. If you have a very large product table, if you code the finish field, obviously it's going to save you some storage space. The other thing you need to think about is how frequently is the finish field accessed. If the customer needs to access the finish field very frequently, you don't want to code it because if you code it when the customer access the product and also want to find out the finish for the product, you have to join these two tables in order to process the query. And that's going to take up some memory and also processing power. You probably don't want to code it this way. But if the finish field is not frequently accessed by the customer, then it makes sense to code it. The other thing you want to think about is how many different types of finishes you have. Well, if you have a lot of different finishes, then it probably doesn't make sense to code it. Because even though you save some space in the product file, you end up creating a large finish table. If you have a field that's very long, for example, a description field, you may want to compress it. If there is a field that's sensitive, for example, the credit card number, you may want to encrypt that field so that in case the file is stolen, the hacker wouldn't be able to read the credit card number. And then the third decision you need to make is how to control the data integrity, making sure that data is consistent. Well, there are a number of things you can do to improve the data integrity. The first technique is to use the default value. For example, when you fill out a form on the internet, when they ask you to put in your address, sometimes they have this default value for country, USA. And the reason is because they know most of the customers will come from the US. By putting the USA as the default value, it accomplishes a number of things. First of all, you don't need to fill out this field if you are from the US. And the second thing is they can be sure that the data is in the right format. When you define the table, you can put a range control for the field value. For example, you can say the price has to be a number between 0 and 10,000. If somebody accidentally puts a number greater than 10,000, then it will alert the user or database administrator. How do you handle missing data? There are a number of techniques you can use to handle the missing data. First, you can substitute it using an estimate of the missing value. Sometimes you can use an average. And the other technique is to construct a report listing missing values. So you can create an exception report to report that, okay, these data are missing, and then the user can determine if that's important or not. And the third technique is you can ignore the missing data unless the value is significant. If the value is not significant, it's not going to make a difference in your analysis, then just ignore the missing data. After finishing optimizing your field, you move on to optimize your record. Okay. Here we are talking about physical records, and they are different from logical records. Logical records are the fields in the logical database design. Physical records are referring to a group of fields stored in adjacent memory locations and retrieved together as a unit. What it means is, on the hard drive, these fields are put next to each other. And when the computer reads the data, it will read them as a group. That's called the physical records. Okay, another concept that's related to this is the concept of page. And page refers to the amount of data read or written in one input-output operation. For example, if this computer's page is 64 kilobytes, that's how much data the computer can read or write in one I/O operation. A related concept here is something called a blocking factor. Blocking factor means the number of physical records per page. So let's say the physical record happens to be 32 kilobytes. All right, so what's the blocking factor? The blocking factor is 2, because the page is 64 kilobytes and the physical record is 32 kilobytes. So the blocking factor is 2. It means that in every I/O operation, the database can read or write 2 physical records. What if your physical record is 27 kilobytes? What's the blocking factor? Well, it's still 2, because 2 times 27 is 54, and you have 10 kilobytes left, but it's not enough to read another physical record. Well, then this physical record is probably not very efficient, right? Because every time you read or write, you are wasting 10 kilobytes capacity here. So, well, one decision you want to make in the physical database design is how you want to organize the physical record so that the blocking factor is going to be an integer multiple. Another technique often used in physical database design is denormalization. And denormalization is the opposite of normalization. Normalization is about decomposing a table into smaller tables, and denormalization is about combining smaller tables into large tables. Why do we want to do that? Well, the reason is because in relational database, the most taxing operation for the relational database is something called join. and that means combining two tables together. When you need to get data from multiple tables in relational database, you have to perform the join operation to combine these two tables into a large table and then read the data from this large table. And that's the most taxing processing for a relational database. And the reason why we want to denormalize the tables in physical database design is so that we can avoid joining the table during runtime. However, denormalization also comes with some costs. First of all, we are going to waste some storage space. When you denormalize the tables, we put two tables together, you're introducing data duplication in these tables. So it will waste some storage space. And also it will threaten the data integrity and the consistency. So you have to take precautions to ensure that the data is consistent in these denormalized tables. You don't want to denormalize unless it's necessary. There are three common denormalization opportunities. One is the one-to-one relationship. The other is many-to-many relationship with attributes. The last one is reference data. Let's look at some examples. The first example is the one-to-one relationship. The student and the application. One student has just one application. If the application data is often accessed with the student information, then it makes sense to denormalize and put these two tables into just one table. So you have one table called student table, and it has application information in it. The reason why a one-to-one relationship is a good opportunity for denormalization is because it doesn't create any data duplication. You see, when you put these two tables together into one table, it actually doesn't create any data duplication. It actually saves some space for you. So now you don't need the primary key and the foreign key anymore. Right? So it actually saves you some space. So that's why when you see a one-to-one relationship, you probably should think about the opportunity for denormalization. Then the second opportunity for denormalization is if you see a many-to-many relationship and also you see attributes associated with the relationship. And so that's what we call the associative entity. In this case, if these two tables, item table and the price quote table, are accessed together frequently, then it makes sense to denormalize these two tables and create a bigger table called item quote. So by denormalizing, now we only have two tables. In the case of requiring information from these two tables, we only need to join two tables instead of trying to join three tables simultaneously. The last opportunity for denormalization is something called the reference data. In this case, we have storage instructions and item. Right? Each item has some storage instruction. So one storage instruction applies to multiple items here. The storage instruction is the reference data because this entity only has a relationship with the item table. It doesn't have any relationship with any other tables. In this case, it sometimes makes sense for you to denormalize the tables and put them together in one table. So this way, you don't have to join the tables if you need to access both the item information and the storage instruction.